All right, so we're going to look at last section in Chapter 7, which is 7.6, solving trig equations algebraically or analytically. So when you're solving a trig equation algebraically, that means that something nice must work out. Maybe you can factor it. Maybe it's a quadratic, something like that. When you can't solve it algebraically, we already looked at some of that stuff back in like section 7.3. We did a lot of graphing. Okay, so no graphing at all today. So some of the techniques we're going to use, I already mentioned. Factoring, writing things in terms of one trig function. So you might get a problem that has sines and cosines in it. Well, we don't want both. We want to try to get just one. Okay, having two trig functions is kind of like having an equation with x's and y's. It's more confusing. There's two different letters. You kind of want to get everything just as one letter. And also using the quadratic formula. So I'm going to show you how to use the quadratic formula on more things than you probably knew you could use it for. Right? Okay. In general, you can use the quadratic formula to solve anything that looks like this. You have something to a power plus something to half that power plus a constant. So you're probably used to solving things like when n is 1. So a 2, a 1 for the exponents, and when there's like an x in the box, or like 3x squared plus 2x to the first plus 6 equals 0. That's like the most basic application of quadratic formula. But even if this exponent was a 4, and this exponent was a 2, still quadratic. Well, quadratic type. So it still falls in the same pattern where the first exponent is double the second. And it doesn't even just have to be x's. I mean, you can use different letters, but I could also change this to sine x and sine x. It's exactly the same way to solve that problem if you wanted to use quadratic formula. A is 3, B is 2, C is 6. You plug those numbers into the quadratic formula, and there's one extra thing you got to do at the very end. Okay. And we'll look at that when we do it. Right. But you can use the quadratic formula on anything that looks like this. Just fill in anything you want in the boxes, but the boxes have to be the same. Okay. Same thing in each box. All right, so let's look at this one. They want to know all solutions from 0 to 2 pi. So this looks like it could be a quadratic kind of problem. But what's wrong though? There's something here that's not good. You got something squared, and then you've got something, and you got a constant. And I'm kind of giving you a hint right below it. Yeah?
The trig formulas aren't the same.
Yeah, they're not the same. You've got a cosine and a sine. What you always want to do is substitute for the one that's squared. Okay? What are you going to substitute? You're usually going to use a Pythagorean identity. Okay, I have them all on the board on the right, but the one that you actually need for this problem is right there. Using this Pythagorean identity, we're going to substitute in for cosine squared. Everything else is going to stay the same. What can you change cosine squared to if you get it by itself in that formula? Yep, Joe?
1 minus sine squared.
Yep, 1 minus sine squared. Now, distribute out the 2 and rewrite it so that it's something squared, something, and then the constant. All right, so we've got 2 minus 2 sine squared x plus sine x plus 1. Now, if I was actually doing this problem, what I probably would have done is combine the 2 and the 1 in this step. Now I need to write it all again just to combine them. So positive 2, positive 1, positive 3. Okay, so let's write it again. Negative 2, sine squared x plus sine x plus 3 equals 0. Now, I'm not sure if this is a problem that's going to factor, but whenever I factor, I don't like the squared term to have a negative. Okay? Usually when you factor something like this. You'd like the squared term to already be positive. So what could I do to all all four terms? It won't have an effect on the 0. But what could I do to all four of them to change that negative in front to a positive? Yeah?
Just factor out a -1.
Yeah, just factor out a -1 or divide everything by -1. Just change the sign of everything. So 2 sine squared minus sine x minus 3 equals 0. Now, the equation that you're trying to solve right there is exactly like solving this. If you can solve 2x squared minus 2x squared minus x minus 3, you can solve the one above it. It's the same thing. All right, so let's try to factor it. Let me just move that down. Would factor into 2 sets of parentheses. And what would be my first term in each parenthesis? Well, think about if you were going to factor this one.
2 and a 1.
A 2. You need a little more. Yeah?
2x and x.
It would be 2x and x, if that's what you were going to factor. So what do you think my first two terms are going to be with this one? It's not 2x and x, it's 2 sine x and sine x. Because if you multiply those out, 2 sine x times sine x is 2 sine squared. Now let's look at our positive negative. We have a negative, negative. So when you factor, what does that mean if your middle term is negative and your constant is negative? Yep.
Your signs are going to be positive at your plus and minus.
Yep, you're going to need one of each. He said positive and minus. It makes a difference which one you put where. I just put them in the order he said. If it doesn't work, we can always switch them. Now I need two numbers that multiply to give me 3. And since 3 is prime, the only option for integers would be what times what? Yep. 1 times 3. Let's try 1 and 3. Let's see what happens. So we get negative 2 sine x times, or 2 sine x times negative 1. That's negative 2 sine. 3 times sine is positive 3 sine. Negative 2 plus 3 is positive 1 sine x. Did we want to get a positive 1 sine x? No, it's close. We wanted a negative 1 sine x. So all I need to do is just switch the signs. Positive, negative. If you're saying, could you have switched the numbers? No, that wouldn't have worked here. You had to switch the signs. Now we get 2 sine times 1, it's 2 sine. Negative 3 times sine, negative 3 sine. 2 take away 3, there you go, negative 1. Right, so that's the hard part. Now we factored it. What do you do with each one of those factors? Yeah.
Set them equal to 0.
Yep, set them both equal to 0. Right, so we've got 2 sine x minus 3 equals 0. Sine x plus 1 equals 0. And now get sine by itself in each one of them. I mean, eventually you want x by itself, but just start with sine. What would sine x equal here if you move the 3 and the 2 to the other side? Yep.
3 halves.
3 halves. What's 3 halves as a decimal? 1.5. How high does the sine function go?
1.
It only goes to 1. It doesn't go to 1.5. So if you try to get rid of sine by taking the inverse sine of each side, the inverse sine of 1.5 gives me an error, which means from this part, I get no solution. Doesn't mean the whole thing is no solution. I still have something else to look at. But there are no angles you can take the sine of and ever get 3/2. That's impossible. All right? And even if you didn't know that, you just type it in on the calculator and it's going to tell you error or domain error is what the graphing calculator would say. All right? If you're using a regular calculator, one of mine, I think it would also say domain error. All right. How about if I get sine x by itself there? What would I do on each side? Yeah. Subtract 1. And now we want to get rid of the sine function by doing what cancels out sine?
Inverse sine.
Inverse sine. So x is the inverse sine of -1. Now if I'm doing that problem, -1 is easy for me because I think of the graph in my head and I think of where it hits the lowest. If you can't always do that, okay? Because sometimes it's not a nice number like 1 or -1 or 0. So the way you do it is you type it in on the calculator. I always do it in degrees first because you're usually going to get a nice answer. If you do it in radians, you're going to get some weird number that's a fraction with pi in it. And my calculator won't tell me what it is. It'll just give me the weird decimal. So do it in degrees first. Inverse sine of -1. Okay, I get -90. Now you gotta be careful because they said to give answers between 0 and 2 pi. So what can you do to -90 to make it positive? What can you add to it? Just add 360 and you're going to get 270. That's the answer they're looking for. So I'll do it in degrees. Or if you convert it to radians, it's 3 pi over 2. So you would have seen the number 4.71 come up on the calculator, and it would have kept going. You probably wouldn't have recognized that as 3 pi over 2. All right. So always do it in degrees first, and then convert that by hand to radians if you need to. All right. So that's where sine equals a negative number. Okay, that's where sine equals a negative number. So let's think if that's going to happen anywhere else. Think of the graph. Does sine ever hit -1 twice from 0 to 2 pi? No, it only hits it once. But let's say you didn't think of that. You're like, okay, I'll try to find the other answer. Well, what quadrant is 270 in?
It's on the edge of the...
It's not in a quadrant. It's on an axis. So that chart doesn't even apply. 270 is in between quadrants 3 and 4. So when that happens, you don't have to worry about using that chart at all because you can't. So at this step, we're done. Right? But I think it's a lot easier if you just think in your head, okay, sine looks like this. It only hits the highest point and the lowest point one time. It doesn't hit it twice. Now, if you said, where does it hit 0? Then I would say it hits it twice. Here and here. It hits it twice. And if you're thinking, well, what about here at the end? Yeah, but that's a repeat of the first one. So those would be the only two. But it didn't ask about 0. So for that one, that's it. 3 pi over 2 is the only answer. Okay, questions on that one? So in the homework tonight, some problems are going to be set up like this. They're going to start you off at this step. If they start you off here, there's not very much work to do. You just take the inverse sine of each side. Very easy. Some problems are going to start you off here. Not as bad as starting from scratch because they're starting you off with something that's already factored, right? So I think there's 2 or 3 problems they start you with factoring, and then there's some problems that just start you like this. from total scratch. So you got to do the factoring and everything. Okay. So that's one of the hardest types of problems. Unless you don't remember quadratic formula, then that would be harder. But if you remember quadratic formula, it's about the same difficulty as this one. All right, let's try this one. Okay, directions are a little different. They're saying find all solutions in one cycle, or in one period. They're not telling you the period this time. Okay? We know how to find the period of this. Okay, we did that before. Period of sine squared is pi. Okay, I just memorized that. Period of sine squared is pi. If you're not sure how I did that, it's sine to an even power, which is the formula pi over b. Okay. Period of cosine is 2 pi. Least common multiple of pi and 2 pi is what? What is it? 2 pi. Right. Least common multiple of 1 and 2 is 2. Okay. Least common multiple can't be smaller than any of the individual ones. So it's 2 pi. So what they're really saying is find all solutions between 0 and 2 pi. Okay. To solve this, what do we want to do first? It's not set up like the last one because it's not equal to what?
0.
It's not equal to 0. Okay, let's get it equal to 0. My suggestion, you might be wondering why I'm going to do this, is put everything on the right. You'll see why in a minute. I mean, you can put everything on the left, but it's going to lead to one extra step. Put everything on the right. So how would you move 2 sine squared to the other side?
Subtract 2 sine squared.
Yep, subtract it. So minus 2 sine squared x plus cosine x plus 1. I'm starting to try to make it look like it should. Putting the constant at the end, the squared term first, and then the term that doesn't have an exponent right in the middle. Now you might be like, why did you do that? You said you don't want squared terms to be negative. Well, watch what's going to happen. This is where we started off last time. Which trig function am I going to substitute for? Because I got 2 different ones. I can't have that. Well, I say no, then that automatically tells you which one. So it's not the cosine, but why is it the sine? Well, what did I say to always substitute for? Yep.
You substitute for the squared term because
Oh,
you have
yeah.
a Pythagorean identity.
Always use a Pythagorean identity on this one, and you can't do a Pythagorean identity with cosine. Right? It's got to have an exponent of 2. So let's fill this in. And now maybe you're going to start to see why I moved everything to the right. What is sine squared using the Pythagorean identity? Yeah?
1 minus cosine.
1 minus
Cosine squared.
cosine squared.
That's what I was saying. Substituting cosine.
Oh, I thought you meant substitute in for cosine. I thought you meant substitute in for sine squared, 1 minus cosine squared. Okay. Now, what do we have to do with that negative 2? Distribute it, and let's do this in one step. What's negative 2 times negative cosine squared?
2 cosine squared.
That's why I moved everything to the right, because I knew that would happen. Not a big deal if you don't, just divide everything by negative 1 to make the cosine squared term positive. So 2 cosine squared x, I didn't forget about negative 2 times 1, I'm going to come back to that, plus cosine x. What's negative 2 times 1? Negative 2 plus 1.
Negative 1.
Negative 1. So I just did it all in one step. And now what I'm trying to solve is something like this. 2x squared plus x minus 1. That's the same type of problem. Now, if you tried to factor this, you would have 2x and x. There's no options there. You would have to have 1 and 1. There's no options there. The only option you have is whether you do plus minus or minus plus. Well, if we did plus minus, does that work? Negative 2x plus 1x. What's negative 2 plus 1? Negative 1. That didn't work. Let's try plus minus. That's 2x minus x. 2x minus 1x is 1x. So that's how it will factor. But I'm not going to write x. What am I going to put in place of it?
Cosine x.
Cosine x. So it's 2 cosine x minus 1 times cosine x plus 1. I already have equals 0. Sorry. My equals 0 is over here. In this first factor, Jacob, what would cosine x be when you get it by itself in the first factor?
1/2.
Yep. So I'm going to come back, and actually, didn't we just, did we do that one yet? No, we didn't do that. So we'll have to figure that one out. All right, so cosine x equals 1/2. And cosine x equals, what's going to be on the other side? Brandon? Negative 1. Yep. Okay, now we're going to solve them. Let's do the inverse cosine of 0.5. Inverse cosine of 0.5, 60 degrees. What's 60 degrees in radians? So 60 degrees in radians is, yeah?
2 pi over 3.
That's 120. So half of what you just said.
Pi over 3.
Pi over 3. Okay, so there's your first answer. Now, you're looking for where cosine is positive. You just got an answer in the first quadrant. All the trig functions are positive in quadrant 1. What other quadrant is cosine positive in? Oh, Nikki? 4. And what's the formula in quadrant 4 to find an angle? 360 minus the reference angle. 360 minus the reference angle? Our reference angle was 60 is 300. Now, to change that to radians, the way I do it, since we already know 60 is pi over 3, 300 is 5 times as big as 60. So just take the answer we already have, make it 5 times as big. So there's 2 answers. Now, whenever something equals a 1 or a negative 1, that's usually going to be a case where you're going to get something on an axis. So let's take the inverse cosine of negative 1. Even if you didn't know it's on an axis, it's not a huge deal. Just type it in and watch what you get. 180, it's on an axis. I don't have to use the diagram to figure out the other answer because there isn't one. So 180 degrees. And 180 degrees in radians is how much? Pi. Yep. So the 3 answers that you get are pi over 3, 5 pi over 3, and pi. Questions on one? This is about how they all pretty much go. I want to try one with a quadratic formula. Okay, this part, just watch this for a second. Remember that technically when you find an answer to a periodic equation, it has an infinite amount of answers. In this section, I don't care about the infinite amount of answers. I want you to remember that there are more answers every cycle, but we're not doing plus the period times n, okay? So we're not finding all solutions, just the ones in a certain window. Questions on that? We've done this idea before, and it's going to come up again probably, well, definitely on the final, where you do plus the period times n, but you don't have to worry about it in this section. Okay, let's try this one. Find all solutions, and this time they were nice, they just said 0 to 2 pi. Now, technically on the last problem, I should have gone back and made sure all my answers are where they should have been, between 0 and 360. They all were. These are all between 0 and 360. If I got one that wasn't, I would have just crossed it out. But I didn't. Okay? So those were all correct. So let's make sure we do that on this one. We're going to check for answers between 0 and 2 pi. All right. This is a quadratic. Doesn't look like a quadratic. There's nothing squared. But there will be. We're going to start with this. How can you rewrite tangent? We have an identity, you can write tangent as something different. Yeah? Sine divided by cosine. Yes. When in doubt, change everything to sine and cosines and see what happens. That's good that Henry got rid of the tangent, but now I don't like that there's a fraction there. How can I get rid of the left-hand side being a fraction? Whatever I do on the left, you got to do it on the right. That's kind of like the homework problem when you multiplied everything by 3. But don't multiply by 3. Yep. Multiply everything by cosine. Watch what happens now. Left-hand side is sine. Equals 3 cosine squared x. Now, it's just like the last two. Except I don't think this one factors. So now I have to substitute for either the sine or the cosine squared after I get it equal to 0. So, do you want to move everything to the left, or do you want to move everything to the right? Which way do you think we should move it? Yeah?
To the left.
I put everything on the left. You're going to be temporarily creating a negative, but it's not going to be there in a minute. So minus 3 cosine squared x plus sine x equals 0. Now, you've got a choice. Which trig function should you plug in for? Cosine squared or sine? Oh, Joe?
Sine. You should plug in sine or cosine. You should
Just tell me which one I should
change
change.
the cosine to a sine.
Change the what?
Cosine.
Change the what?
Cosine.
The what?
Cosine.
What else is there?
The sine.
No, with the cosine.
Cosine squared.
Squared, yes. The trick is to remember you always substitute for the squared one. That's why I want you to say squared. Wherever a term is squared, change that. Now, we have to decide what we're going to change it to. What is cosine squared? And the goal is to rewrite it with sine, because you want to get all sines. Yep? 1 minus sine squared. Okay, now distribute, and let's see what we get. We're going to get a negative 3. I'm going to put that at the end. That's my constant. Positive 3 sine squared plus sine x minus 3 equals 0. Now, that doesn't factor. So the other way to solve a quadratic if it doesn't factor is to,
Quadratic formula.
quadratic formula. Now, I'm not going to tell you the extra step you have to do right now. I'll tell it to you later. Let's just do this like it was a quadratic, regular quadratic. What's A, B, and C? Yes. What are their numerical equivalents in this problem? Yes.
3, 1, and negative 3.
The heckler has a correct answer. 3, 1, and negative 3. Those are A, B, and C. Now fill them into the quadratic formula. Go through everything just like you normally would, and I'll tell you what you have to do at the very end. What's the first thing we write in the quadratic formula? Yeah?
Negative b
Negative.
plus or minus the square root of b squared minus 4ac over 2a.
And I did all that as he told it to me. Now do all that. You have minus a minus, so just make that a plus. So it's the square root of, what's 4 times 3 times 3? 36 plus 1 more is 37 over 6. Now, if this was a regular problem, 3x squared plus x minus 3, it'd be done. Okay, there's one extra thing we have to do with that. If this, let me just go here for a second. If this was the problem, and you just did all the arithmetic we did, what would you have just solved for? Well, what would you, you would say, what is this? This is it is the root, but it's also the what?
X value.
It's the x value. You just solved for the value that I'm pointing to. Okay? If that was the problem, there's your answer. Now, that wasn't the problem. This was the problem. So, what do you think we just solved for? We haven't quite found x, but we're very close. Yeah? We just found sine x. So that is equal to sine x. So now this is the extra step. What would you do to make that x instead of sine x? Yes?
Inverse sine.
You take the inverse sine. So x equals, and we will do this out. Inverse sine of 1 plus or minus square root 37 over 6. Now, I said that you can only take inverse sine if the number is between what and what. Like we did one earlier that was too big. We did inverse sine of 3 over 2 or 1.5. It was too big. This has to come out between what two numbers? Yep.
-1 and 1.
-1 and 1. All right, let's look at the plus first. Let's take 1 plus the square root of 37. Yeah. Let's try again. 1 plus square root 37. I get 7.08. That's the top.
Wasn't there a negative sign?
Yes, there is. I'm doing the plus first.
Not from that.
Oh, yes, that makes a big difference.
Okay, Joe.
Thank you. Let's type it in again, except let's make it a 1, -1. So now the top is 5.08, and we're going to divide that by 6. Is that a number that I can take the inverse sine of?
Yes.
0.847? Sure. It's between -1 and 1. So second inverse sine, you could just type in 0.847, or just do second answer, and it'll do the last answer that was on the screen. So, in degrees, I really want it in radians though. So degrees, it's 57.900. Or, if you want it in radians, let's do the inverse sine. And now I have to actually type it in. I can't do of the last answer, because the last answer is 57.9. I want the answer before that. 0.847, 127. Close enough. So in radians, it's 1.01. Alright. And now remember what it was. It was 5.08 divided by 6. It was 0.847. Is that a positive or a negative number? 0.847.
Positive.
Positive. What other quadrant is sine positive in besides quadrant 1? 2. Once you have your reference angle, how do you get an answer in quadrant 2? What do you do with it?
Pi plus the reference.
Pi plus the reference is for quadrant 3.
Pi minus the reference.
Pi minus the reference angle. Pi minus 1.01. You always have to remember to use that chart. 2.13. So those are the answers from just doing the plus. Let's look at what happens when we do the minus. You've got negative 1 minus the square root of 37. So it gives me a numerator of negative 7.08 divided by 6. Negative 1.18. Can I take the inverse sine of that?
No.
No, it's too small. So in this problem, you don't even have to worry about the negative. It doesn't work. If it did work, then you would have gotten 2 more answers. Okay? Just like we got 2 answers here. But it doesn't work, so you're done. Right? So that's about as bad as they get when you have to do the quadratic formula. Although some people don't. They like that better than factoring. Depends on what you like better. But any questions on that? Okay. I think this one it's very similar to ones we already done. There's nothing new here to really explain or learn from. Okay, let's try this one. Find all solutions in one period. Okay, so first step is always to get it equal to what? See? Yeah, let's get it equal to 0. And then we'll go from there. Let's bring everything to the left. So I have 3 tangent to the 4th. That's going to stay right where it is. How about, Kim, what do I have to do to move the 2 things on the right over to the left?
Put 1 plus secant squared x.
Yep, I want to move both of them.
Subtract.
Subtract them. So let's minus the secant squared. And minus the 1. Now, does that look like it almost fits a quadratic pattern? Remember I said as long as the first exponent is double the second and you have a constant at the end? But it's not quite. Why isn't it quite a quadratic? What's wrong here that we've already dealt with 3 or 4 times before? Yep.
They're not all set to the same trig function.
They're not all the same trig function. So Joe, which one do you substitute for? Yeah, I'm pretty sure. Which one do you substitute for?
We go with the tangent 4. That's what I mean.
So which one do we always...
Secant squared.
Yeah, we always substitute for the one that's squared. Okay, so you always substitute for the one that's squared. You always substitute for the one that's squared. Okay. The one that's squared. All right. Just whatever you substitute, leave it in parentheses because there's a minus out in front of it. So maybe we should have put everything on the other side, but we can fix the signs if we need to. What is secant squared? And we're going to hope that when we use a trig identity, we end up with tangents. If we don't, we're stuck. What is secant squared? Yeah?
1 plus tangent squared.
It's 1 plus tan squared. That's going to be perfect. It's exactly what we want. So now we have tangent, tangent. One exponent's double than the other. We're good. Okay, let's do what we've got. 3 tangent to the 4th. And actually, you know what? I think we put everything on the correct side because you want the leading term positive when you try to factor, and this will factor. Minus 1, minus another 1. That's a minus 2. So I just combine the minus 1 and the other minus 1. And the minus tan squared goes in the middle. Okay, Let's see if we can factor it. What you're trying to factor is just like factoring this. If you're going to factor the one at the bottom, what would be your first two terms? Like you could multiply what times what and get 3x to the fourth. And you got to use this. You always, when you factor, you've got to use the term in the middle somehow to get the first term. Yep.
3x squared, x squared.
You would do 3x squared and x squared. We're going to do 3 tan squared and tan squared. That's exactly how we're going to start. 3 tan squared, tan squared. Now the rest is going to be exactly the same. It's going to be exactly what you would do on the bottom. What would your signs be? You have a negative middle and a negative constant. Yeah, Damien?
Positive, negative.
Positive, negative. It does make a difference which one you put where. I'm just putting them in the order he said them. And now two numbers that multiply to give me 2. Robinson?
Oh no, I was just moving my hand. I was.
Oh.
Well, 2 numbers to go to.
Yeah.
1 and 2.
Yeah, okay. 1 times 2. So 1 times 2 gives me 2. It makes a difference which ones I put where. I would do something like this. Let's check it. 3 tangent squared times negative 1. That's a negative 3 tangent squared plus a 2 tangent squared. Negative 3 plus 2 is negative 1. Perfect. That's what we want. Okay. Now set each factor equal to 0. Minus the 2, divide by the 3. You can write that out in multiple steps, but that's all you really need to show. That's all I'm going to look for on the test. How about this one? Tangent squared x would equal 1. Now, I have tangent squared. I can't even do inverse tangent yet because I got to get rid of the square. What's the first thing I would do to get rid of the square? Take the square root. Square root, square root, square root, square cancel. So the tangent of x equals the square root of negative 2/3. Now what? But what are we trying to get by itself?
X.
X. What's preventing it being by itself?
Tangent.
Tangent. So
Inverse tangent.
get rid of tangent with what?
Inverse tangent.
Inverse tangent. That's normally what I would do. I would do inverse tangent. It's normally what I would do. But, look at that. What's on the board doesn't like you. It's upset. Bless you.
Yeah, it's an imaginary number.
What do you mean? What do you mean it's imaginary?
You have the square root of a negative. It's I square roots of 2/3.
You have an imaginary number. It's the square root of a negative. We're not dealing with imaginary numbers. So this has no solution. You can't take the square root of negative 2/3. If you could, then you would do inverse tangent, which is exactly what we're going to do over on the right. Right? So first thing I have to do is get rid of the square. And to do that, I square root. So take the square root of each side. What's the square root of 1? 1.
1.
What else? Everyone always forgets about the other one.
1 and or negative 1.
1 and negative 1, yeah. 1 times 1 is 1. Negative 1 times negative 1 is also 1. So we're still going to get 2 answers because of that square root being positive and negative. If you forgot the positive and negative, you just lost an answer. Now, what do I do on both sides to get x by itself?
Inverse tangent.
Inverse tangent. So x equals inverse tangent of 1 and negative 1. Let's do it in degrees and see what we got. Inverse tangent of 1. That's 45 degrees. Or pi over 4. Now I want to make sure that I'm between what I'm supposed to be. I'm supposed to be between negative pi over 2 and pi over 2. That's negative 90 to 90. Is 45 between those two numbers? Yeah, so that's fine. That's good. All right. Now, where is the other quadrant that tangent would equal a positive number? I just got an answer in quadrant 1. Where else? Yeah? 3. The angles in quadrant 3 start at 180 and they go to 270. Is that going to be in those numbers? No, that's negative 90 to 90. Answers in quadrant 3 are beyond this. So we don't have to worry about doing the second answer. If I wanted to do it, I would do 180 plus 45. That would be the other answer. But we're not doing it. I'm just reading the directions. Okay, other answer. Inverse tangent of negative 1. I get negative 45. Is that between these two? Yeah, negative 90 to 90. Negative 45 falls right in there. So, yeah. Now, we just found a negative answer. Where else, what are the two quadrants where tangent is negative? Yep. 2 and 4. That's an answer in quadrant 4. Negative 45 is the same as 315. So you already got a quadrant 4 answer. Do I have to worry about the quadrant 2 answer? If you're in quadrant 2, what are your angles between? Because that's where the other answer is. I'm just wondering, do I need it?
90 and 180.
You're between 90 and 180. The directions said negative 90 to 90. So because of that, you don't have to worry about the second answer. Right? So both times the second answer was eliminated because I read the directions. Okay. If I wanted the second answer angle, I would have done 180 minus 45. That would have been the other answer. But they don't want it. Alright, so we got 2 left, and out of the 2, this one's a little trickier, but it does factor. There's no quadratic formula. Anytime you see 4 terms, okay, remember, terms are separated by plus and minus signs. 1, 2, 3, 4. That's usually where you're going to try factor by grouping. So factor by grouping is where you just take out what you can from the first 2, take out what you can from the last 2. The first 2 things I underline, what do they both have in common? Yep. Cosine x. So it's almost like you're just going to cover it up. If I take cosine x out of the first term, all I'm left with is 2 cotangent. If I take cosine x out of the second term, what am I left with?
Negative 3.
Negative 3. So the goal with factor by grouping is to get this again. That's what you want to happen. So let's see when we do the second part what happens. Okay, what can I factor out of the last 2 terms? They don't have much in common, but they have something. Yeah? They have a 3 in common. 3 times what would give me 6? 2. Cotangent x. 3 times 2 cotangent x is 6 cotangent x. 3 times what is negative 9? Negative 3. And we got exactly the same thing that we just got before. That's what always happens in factor by grouping. Now, this is your first term. This is your second term. They both have in common what's in the parentheses. So now factor that out. 2 cotangent x minus 3. If I factor that out from the first one, what's the only thing left there? Cosine x. And if you factor it out from the second one, what's the only thing left? 3. Now, on the left-hand side, all you have is one term. Something times something equal to 0. Set each factor equal to 0. Let's start with the one on the right. What would cosine x equal? -3. What's the inverse cosine of -3?
No.
No, can't do that. You can only take the inverse cosine if it's between 1 and -1. If you try it, you're going to get an error. So this whole part doesn't matter. So there's no solution from that. Let's look at this one. What would the cotangent of x equal?
1.5.
1.5 or
3/2.
3/2. But we don't want cotangent x, we want x. So how would you get rid of the cotangent function?
Inverse cotangent.
Inverse cotangent, I agree. What's the problem with trying to do inverse cotangent?
You don't have a button.
There is no button for it. So we have to rewrite this with a different trig function that we have a button for. What trig function is very similar to cotangent? Tangent. What's the relationship between cotangent and tangent?
It's the inverse.
They're not the inverse.
Reciprocal.
They're reciprocals, which, what does that mean simply? Flip it. So just flip each side. Flip what's on the left, and you just turn cotangent into tangent. Flip what's on the right. There you go. Now you've got a problem you can solve. What do I do on each side now to get rid of the tangent? Inverse tangent. So let's do the inverse tangent of 2/3. It's not going to be a nice answer, so I'm not going to do it in radians first. Inverse tangent of 2/3, 0.588. Tangent equals 2/3. What kind of number is 2/3? It's a fraction. What else? Positive. We just got an answer in quadrant 1. Where else is tangent positive? 3. How do you get an answer in quadrant 3? Pi plus reference angle. Pi plus reference angle. 3.7. We'll just say 3.73. Now, just going to go up and make sure there weren't any directions. Find all solutions in one period. All right. Period of cotangent is pi, 2 pi, 2 pi, pi. What's the LCM of pi and 2 pi? 2 pi. So you should be finding all answers between 0 and 2 pi, or 0 and 6.28. Are those answers between 0 and 6.28?
Yes.
You're okay then. Okay, questions on that one? All right, last one. This one's a little easier than the last one. The factoring is much easier. Well, I think it's easier. What's different about this one? We haven't had anything like this in any problems we've done today yet. Well, the trig functions are the same, but, yep,
There's 2 inside of it.
there's a 2 inside here. That's a problem. Even more important than having the trig functions the same is to have these the same. So how can we rewrite sine 2x so that the 2 is somewhere else? I can't have it inside. Yeah?
2 sine x cosine x.
Yep, that's an identity from yesterday. 2 sine x, cosine x. Now you have an x for the argument, x for the argument, another x for the argument. You might be thinking, yeah, but now we got a cosine in there. Isn't that bad? That's okay. That's not going to be a problem. It's more important that you have the arguments all the same. Okay, what do we want to get it equal to?
0.
0. So let's put the sine x on, let's put this on the other side. Now, if you factor the left-hand side, it's kind of like factor by grouping. All you can do is factor out what they have in common. They only have a sine x in common. So sine x. What's left in the first term? 2 cosine. Now, you can't say that there's nothing left in the last term. If you block it, it's like there's nothing else. You got to put something there. So you put a 1. And now we have something times something equals 0. So take each factor and set them equal to 0. So we have that. And what's cosine x going to equal? 1/2. Now, cosine x equals 1/2. I know we already did that one earlier. I'm just going to go back. And it's not cheating. It's using what I've already done. I'm using my own work. My work. Cosine x equals 1/2. Pi over 3, 5 pi over 3. So we've already gone through those answers. What did I just say? Pi over 3, 5 pi over 3?
Sure.
Now, where sine equals 0, 2 ways to think about it. Personally, I would just think of the graph. Where does sine hit? Well, it hits it here, and it hits here. Where is this point? 0. It's a y value, or it's an x value of 0. What's the x value here? Pi. It's exactly halfway through the cycle. This is one that could be a little tricky, because if you use the calculator and take the inverse sine of 0, watch what you get. Inverse sine of 0, you get 0. But that chart doesn't tell you really how to get the other answer, because 0 isn't in a quadrant. So think of the graph. Okay? Think of where the graph hits 0. It hits twice, at the beginning and halfway. Why didn't I include that one? I mean, that's a third time. That's a repeat of the first one. It's starting its next cycle. Okay. So that's 7.6. Okay, so as I said, tomorrow's section 8.1, totally different, but it's much more, I think it's much easier to understand because you've got triangles and you're just finding the sides and the angles. It's much easier, and it's about 45 minutes. It's shorter. It's pretty much the same.
That's like, 16.
So 1 through 14, 16, and 19. Numbers 10 and on. So like 10 through 14, 16, and 19, those ones are the ones that are a little harder. 1 through 9, they either already factor it for you, or they just give you something like this. And you just take the inverse sine of each side and you're done. So the first 10 questions are pretty quick.